Hello, this is Ira. Now in this second part, we're gonna go over the problems from the fluid static dynamics 183006. And we are still using the NRC Generic Fundamentals Examination Question Bank from May 2020. Okay, the first one. So I'm just gonna go over, the concept ones. So this one is asking about the possibility of water hammer in a liquid system is minimized by, remember, venting systems prior starting centrifugal pumps, right? We talked about a lot in the concepts part about venting the system and how important it was. So to us, it's gonna be, very, very important answer, right? Because that's the answer. So the other one is asking about which one of the following methods will increase the possibility and or severity of water hammer. So starting the centrifugal pump with the discharge valve fully open, that's going to increase because remember that we talked to in order to decrease, right, the severity of water hammer, we need to start the CP pump throttle or closed. So that's what's going to so obviously this one clearly is open, so that's going to increase, the possibility or severity of water hammer. We know that this one will decrease or venting the fluid. We just answered this question about venting the system prior starting a CP pump. So we know this ones are going to decrease and the possibility, and this one will increase the possibility or severity of water hammer. Now, this other question. A sudden stop of fluid flow in a piping system. We know that a sudden stop and flow in a piping system is gonna give us water hammer, but this one says due to a rapid closure of an isolation valve will most likely result on. So we already look at that. We know that that's gonna be a water hammer. Now the next question is one reason for keeping condensate out of the steam line is to remember that we talk about the condensate, what we need to remove the condensate, and this one is to prevent water or steam hammer. This next one, so the possibility of water hammer will increase by condensation in the steam line just prior initiating the flow, because we should not have condensate in the steam line, right? So we know what we cannot have. Okay, so now to minimize the possibility of water hammer when initiating flow in a system, the operator should bend the system prior initiating flow, right? So that's what the operator needs to do. Next, which one of the following describes why large steam lines are gradually warm instead of suddenly admitting full steam flow? So why do we gradually warm? And we talk about that, right? We need to warm the steam lines if we're gonna add some steam flow, because we don't want to have these pressure spikes, right? We're trying to avoid those pressure spikes. So to minimize the potential for water hammer in the steam line, so that's why we do that. Now, which one of the following will minimize the possibility of water hammer? Draining condensate out of steam lines before initiating flow line. That's basically the same. So now, which one of the following operating practices minimizes the possibility of water hammer? So we talk about having the valve throttle or close. So yeah, so preferably having the valve throttle. So starting, the CP pump with the discharge valve throttle. We didn't talk about positive displacement pumps. So we're gonna go with this one. So now, which one of the following will result in a higher probability and or severity of water hammer in a flowing water system? So, okay, so again, which one of the following will result in a higher probability and or severity of water hammer in a flowing system? So shorter valve stroke times rather than longer valve stroke line, because this has like a longer time to dissipate than this one, right? So now we're starting now with the problems section. So now this is gonna be important because there are several questions with this. There are a lot of questions that are similar to this one. So let's take a look at this one. This one says an 85 GPM gallons per minute leak to atmosphere has developed from a cooling water system that is operating at 100 psig. So we have a leak of 85 gallons per minute in a cooling water system at this pressure. Which one of the following will be the approximate leak rate when the system pressure has decreased to 50 psig? So what I do is, okay, I know that 85 GPM is volumetric flow rate. That's my initial volumetric flow rate. And how can I relate this? So I know that I have this formula. Volumetric flow rate is going to be proportional to the square root of the differential pressure. So that gives me the idea, oh, I can use this formula and use this relationship. So I know that my 100 psig is going to be my differential pressure, and they're giving me this other, final differential pressure. So what do I need to calculate? I need to calculate my volumetric flow rate final, right? Now the answer that is asking is for volumetric flow rate is in gallons per minute. Okay, so now what I do is just substitute in my equations, but remember, this is okay to have them in psig, because it just cancels out the units, so it's okay. So the answer is 60.10 or 60.1 gallons per minute. So answer D is the correct one in this case. Now, the next one is just another concept, and it's telling me like the mass flow rate equals volumetric flow rate times. Remember the formula? Mass flow rate equals density times volumetric flow rate. We already looked into that one, so we know that one is that, or it can be, remember this one? The specific volume, it can be, oops, I put it backwards, sorry. Volumetric flow rate over a specific volume. So that's what we have. So yeah, so the answer is gonna be the density. Now this other ones are like similar. We're gonna use this equation, so we just need to, we have many of those, and those ones, they have a lot of them for us to practice. So now we have this other question is a little bit more complex, right? So question P3780. So it says, which one of the following describes the relationship between the main steam mass flow rate leaving the steam generator and the main feed water mass flow rate entering the same steam generator at a steady state power operation? Remember what we talked about steam generators, right? What comes in has to come out, right? So that's what we're trying to do. So it says, again, which one of the following describes the relationship between the main steam mass flow rate leaving a steam generator and the main feed water mass flow rate entering the steam generator at a steady state power operation, right? So assume no other addition or removal of steam generator inventory. So in this one, what we are trying to do is, okay, so what is the situation with this, mass flow rate? If I go over the question C and D, they're basically the same. They only differ in this part. So let's take a look at those ones, smaller and greater. So this one says, the main steam mass flow rate is smaller or greater than the main feed water mass flow rate by the amount of the moisture removed by the steam generator moisture separators. So the moisture separators, where are they in our steam system? So the moisture removed from the steam generator is not the same as the one from the moisture separator and the reheaters, right? that moisture that we talk about is gonna be returned to the downcomer. So that's what we talked about, right? And that's how we kind of like keep like the same level in our steam generator. That's why we are able to keep this, whatever comes in comes out, right? So we know that this one is not correct, right? So we know, okay, so this one doesn't make sense. It's not correct. We can say, okay, these ones are a no-go. So now let's take a look at B. It says the mass flow rates will be the same only if the reactor is operating near rated power. Well, we know that that's also not correct because, I mean, we change the power level every time we have to. So, or level in the steam or the mass flow rate is not going to be depending on, if we run the reactor at a certain power level or not, because then imagine it will be completely hard to calculate all of that. So, no. So finally, the answer is the mass flow rates will be the same only if downcomer level is constant. Yes, and that's what we're trying to do, right? So what we're trying to do is, we're trying to keep the steam generator water level constant at different power levels, right? Trying to ensure that the steam and the feed rates are gonna be equal. So what comes out, whatever comes in, is gonna be the same in our steam generator. That's basically what it's trying to say. It's just in different words. Now the next one, question P 5342. So this one is saying a heat exchanger has the following initial.
I found this on the web for Hussein. Check it out.
Yeah, now my my Siri is spying on me. I don't know how to make it stop. Please don't spy on me. Anyways, let's go back to our question P5342. So we have a heat exchanger and it has the following initial cooling water inlet temperature and it has differential pressure with this parameter. So we have initial system and we have like a final. Let's say this is our initial and this is gonna be our final. What is happening here? So my inlet is 70 Fahrenheit and I have my heat exchanger differential pressure is 10 psi. Later, 6 hours later, so I'm comparing, right? So 6 hours later, the current heat exchanger cooling water parameters are 85 for my temperature, 85 Fahrenheit, and my heat exchanger differential pressure is gonna be 10 psi. So what am I seeing here? What I'm seeing is that I have an increase in temperature, right? But I have the same differential pressure, right? So I'm comparing. It says, so I know what's happening, right? So what is this asking? Now that I know what's going on, so it's giving me this temperature and it's giving me the differential pressure. So since it's giving me the differential pressure, I know that this question has to do with differential pressure, right? So I need to find a formula that has that. So I know that the volumetric flow rate is going to be proportional to my differential pressure here. Okay, so I know that. But then it's saying, okay, the cooling water inlet temperature, we're talking about temperature here. But okay, let's move on because that's all I can figure out with this information. So next is telling me, in comparison to the initial cooling water mass flow rate, now I know that I have mass flow rate, okay? So I know that I'm gonna use this formula. So my mass flow rate from my cooling water is gonna be equal to the density, and this density, guess what, has to do with temperature, is gonna be affected by temperature. So, and I know that my formula, I can multiply my density times my volumetric flow rate, but I know that my volumetric flow rate is proportional to my differential pressure. But okay, now what is this asking me now? So is asking me, okay, what is the current mass flow rate, right? So now that we figured that out, this thing with the questions that we have here, let's try to figure it out. What's my flow rate from my cooling water system? So I know that my differential pressures are the same, right? My differential pressure is not changing, but I know that my temperature is increased. Since my temperature is increased, how is this affecting my density? It's decreasing my density, right? So this makes my mass flow rate decrease, right? So then I know that my current mass flow rate is gonna be decreased. It's gonna be lower, right? It's not gonna be the same. It's not gonna be higher. So it's lower, but because it decreased, because the density of the cooling water has decreased. Yes, exactly that. I can see it, and the temperature increase causes a decrease in my density. So that's totally correct. Okay, so now the next ones are similar to this. This other one is just similar to the other question that we just saw. Now let's take a look at this one. This one is just basically a review of the conversion units from 183.001 units section. But let's take a look. How do we solve this one? This one says reactor coolant system RCS hot leg temperature is constant at 568 Fahrenheit, while the RCS temperature is decreasing due to a small reactor coolant leak. So I know I have this. It's the only thing that I'm giving basically. So it says which one of the following RCS pressure ranges includes the pressure at which the two-phase flow will first occur in the hot leg. Okay, so since it's giving me the temperature, what I have to do now is going to my steam table, right? I'm giving this, if the only thing that I'm giving is a temperature, I can check my saturated pressure at this temperature, and that's gonna be 1207 psia, but it's gonna give me the answer in psia. I need it in psig, so I remove 15, and that gives me 1192 psig, right? So you just need to make sure that this number is within the range, and that's gonna be in the range of 1200 to 1151 psig. So that's gonna be the right answer. So this other one is similar to the previous one that we talked about conversion, similar to conversion. Now this is a review of the moisture one. So let's take a look at this one, P7649. It says, if the quality of the flowing steam water mixture is known, what additional information, if any, is needed to determine the percent moisture content of the steam water mixture? They're giving us the quality. I immediately know, because I know the formula, that if they give me the quality, I can get the moisture. So I don't need any additional information actually, because I know the formula. It's a very easy conversion here. So yeah, I don't need any additional information. I don't need to know the mass flow rate, the specific volume, or the pressure, or temperature, or anything. Okay, now let's take a look at this other one. This other one, it's gonna be maybe a little bit more interesting. This is the one that we took a look at the shrink and swell for the steam generator. We just need to remember, like in this one, in order to solve this question, we just need to remember one thing, and I'm gonna go over that. Okay, so the question is P7689. A nuclear power plant is initially operating at a steady state 100% power. So they just throw a lot of extra information there, right? Get us confused and make us feel like, oh, this is too complex. Just pay attention to, the cues here. So if an unplanned load rejection, right? Unplanned load rejection. So what's happening here? We have a load rejection. So meaning that we are decreasing the steam demand. We have some turbine rejection. Demand, this happens when the demand decreases, right? And it causes the main generator load to rapidly decrease to 90%. The voids in the two-phase flow in the steam generator to bundle region will either shrink or expand. So meaning shrink or swell, right? We have a decrease in demand, so that means that it's gonna shrink, right? It means that the voids are gonna shrink. That causes indicated steam generator water level. So if we have a decreased demand, right? If we decrease the demand, we are decreasing the level, the steam generator water level, right? It's gonna initially decrease. So as long as we remember that, I think we are gonna be okay. Decrease demand. So if it shrinks when we have a decrease of demand, and the water level will decrease, right? And we already went through all the explanation for this one. So now we're gonna have another question. Similar, question P7740. This question says, a nuclear power plant is initially operating at a steady state 80% power. If a control system malfunction causes main generator load to rapidly increase to 90%, what is happening here? We have main generator load increasing, right? It doesn't matter, it's increasing. It can increase to 90%, 95%, 100%. Is increasing, right? And it's asking, the steam voids in the two-phase flow in the steam generator to bundle region will initially, right? Here we have two options, are gonna initially either shrink or expand. Remember, the expand is swell. So since I have a increase in my demand, I know that they're gonna swell, and that causes the indicated steam generator water level. Since I have a demand increase, my water level is gonna increase, right? So I'm gonna swell, I'm gonna increase. If I shrink, my lower goes down on my water level in my steam generator. That's kind of like how I, remember these questions. Okay, now let's go over another problem, a little bit different, changing a little gear here. This question is P581. A nuclear power plant is recovering from a loss of offsite power that caused all reactor coolant pumps, RCPs, to stop. Okay, so I have a loss of offsite power, and that caused my RCPs to stop. My RCPs are here in my primary, and they are the ones cooling and transferring this like heat to my steam generator, right? So what's happening? So if I don't have circulation in here because I lost my RCPs, remember what we talked about, this is gonna get hotter. It's not transferring any heat. It's gonna get hotter, hotter, hotter. And this other side is gonna get cooler, cooler, cooler. Remember that we talked about that. So that's what's happening. When we read that, we need to be able to determine what's happening. So we are increasing the temperature on the steam generator, right? Okay, so now the pressurizer level indication is of scale high. The subcooling margin in the reactor coolant loop and reactor vessel is 100 Fahrenheit. So that means that is low, that means that is cooling, right? Because the reactor vessel like being 100 Fahrenheit, that's cool. Okay, so now, which one of the following is most likely to occur if the steam generator temperatures are 50 degrees Fahrenheit higher than their associated reactor coolant system loop temperatures when an RCP is restarted? So this is important, right? I think if we know, because there's There's always like a lot of noise in the question. So to me, it's like, I know this is important, right? I understand that. So pressure level indicating off scale high, right? I have a pressure spike here. If I restart, this is important. What's gonna happen if I restart my RCP, right? If I restore my IRCP, I'm gonna have a pressure spike, right? Because as I mentioned initially, this area is gonna be very hot and the other area is gonna be very cold. I mean, cold, like, yeah. I mean, it's not as cold as we think, like inside of the refrigerator, that's not, but it's colder than this other side comparison. So we're gonna have this thermal shock, right? If we're trying to mix this, it's like when we have this pipe system, we need to bend, the pipe system, right? Or we have condensation in a steam line, right? We need to vent it, we need to warm it, and we need to make sure that we don't have any condensate, right? Because that's gonna create this pressure spike. Is the same thing, but in like a real world example for a nuclear power plant. So what's going to happen? We're going to have a large pressure spike through the RCS, right? And we said that that's like a safety issue. We need to make sure that that doesn't happen. We need to warm the system. We need to do different things in order to make sure that we don't have this happen. Okay, now the next one is P4042. It says, refer to the drawing of the two lengths of 6-inch diameter pipes, so they are both the same diameter, each containing an identical automatic isolation valve. The actual pipe lengths are proportional to their symbols in the drawing. Okay, they have same diameter. That's what I gather from that. So water at 65 Fahrenheit is flowing at 1000 GPM through each pipe. Okay, so they have at each pipe we have the same, right? The same everything, the same flow, the same temperature. So if isolation valves A and B instantly close, the pressure spike experienced by valve A will be. And this is interesting because when we talk about pressure spike, remember that pressure spike is going to be a function of the mass flow rate, right? So we talk about that when we took a look at this concepts, right? Pressure spike is going to be a function of the mass flow rate. So since we have everything the same here, same temperature, the same volumetric flow rate, so what's going to happen, right? What's going to be the pressure spike experienced by valve A compared to B is going to be the same, right? It's going to be equal to valve B. They are both going to be the same because they have the same volumetric flow rate. Okay, so the pressure spike will dissipate. He's talking about dissipating. Which one is going to dissipate faster? Remember that we talk about like the pressure spike is gonna dissipate faster in a shorter bulb. So we know that it's gonna dissipate faster in B in the shorter line. Okay, because everything is the same. Okay, so that was simple. Now let's take a look at question P6242. Here things start getting a little bit more interesting. Okay, so this one is also the same drawing. We have two length pipes with the same diameter. I don't care if it's 16 inch, 6 inch, whatever, it's the same diameter, right? Everything is identical except the length. Water is flowing at 100 GPM through each pipe. So they both have the same volumetric flow rate, okay? So, and it's asking us to consider two cases, right? Case one, the water temperature upstream of both valves is 65. So we have the same volumetric pressure, right? So in case one, they have in both we have the same volumetric flow rate, right? But the temperature is the same on both ones. So we have the same mass flow rate for both ones in case one. That's what's happening. So I just want to understand what is happening before I even go to the question. I just need to understand what is this telling me. Okay, so I know what's happening here. Everything is the same. Both have the same mass flow rate for case one. Now, case two. Case two states, so the water temperature is 65 Fahrenheit, degrees Fahrenheit on bulb A. So bulb A has this, right? And then bulb B has a higher temperature. So comparing this this one has a low temperature, meaning that I have a high density, meaning that my mass flow rate is going to be high in this one compared to this other one. This one has a higher temperature compared to this one. Therefore, my density is going to be lower and my mass flow is going to be low. Okay, so I know this one comparing each other, bulb A has a higher mass flow rate and bulb B has a lower mass flow rate. Okay, what is the question? It says, for which cases, if any, will bulb A experience a pressure spike that is greater than the pressure spike at the bulb B? And remember, mass flow rate has to do with pressure spike. So it's just asking me about the mass flow rate. When it says pressure spike, that's what it's asking about, the mass flow rate. So I know that for case two, bulb A is going to be a higher mass flow rate or a higher pressure spike. So yes, for which case? Only for case two, right? That's how it's going to work for this one. Okay, so that was easy. So now let's go over another question. But there's going to be another question that is going to be similar. This one, I won't spend too much time on it. So it says P279 says a centrifugal water pump was returned to service after maintenance. However, the operator failed to bend the pump. We know that's bad because we know that we need to bend the pump before we start it, right? We know that we need to bend it. So compared to normal operating conditions, after the pump is started, the operator will see if we have some air, we're gonna see a lower flow rate. The flow rate there's not gonna be that much flow rate because we're gonna have a constriction of air or something in there, so we're not gonna have that much flow rate. So the flow rate is gonna decrease, right? And that means that the discharge head is gonna be lower in this case, right? So that's why we need to make sure that we bend the system, the pumps prior, right, prior operation, so we can make sure that all the air that is trapped there is removed, right? Because what we're doing is the water is displacing, right? The water will be displaced by this air that is trapped, and therefore it will reduce the pump capacity. Okay, next question. P3481. P2481 says, refer to the drawing of a cooling water system. So we have this drawing of the cooling water system. But what is this asking, right? In order to know how it's affecting my system. So, okay, let's take a look. It says Centrifugal pump A is circulating water at a X temperature. It doesn't matter. It's just circulating water at a certain temperature. It can be 80, it can be 90, it can be 100, 101, whatever you want. Which one of the following will cause the centrifugal pump to operate closer to a condition in which gas vapor binding can occur? Okay, so when does vapor binding occurs? So vapor binding in a pump, or gas or bubbles, they're gonna form at the eye of the pumping pillar in a pump, right? They're gonna form here, the bubbles at the eye of the impeller. And remember that we talked about the net positive suction head. So we talk about net positive suction head available has to be greater than the net positive suction head required, right? And we have this pressure, and this is the pressure of the vapor. This is suction, this is discharge, this is the eye, and this part is gonna be my net positive suction head available, and here is gonna be my net positive suction head required. It's gonna be calculated. So we know that stuff, right? So it's giving us different options that we need to analyze. It's telling us that the storage tank level is raised by 5%. So here, this one, the storage tank is raised by 5%. So since this one is raised, remember that we talked about it. We have a tank, is the net positive suction head available. We're gonna have a height of our tank. So when we increase that, we are basically increasing the static head available. So the head, and I'm gonna use this. So head of the height, we are increasing it. So that means, we are increasing the suction pressure, and that's going to give us a higher saturation temperature, basically. So we're going to be more like this in this part, right? So we're going to be farther away from cavitation if we increase that, okay? That's what I went over, like what is affecting the net positive suction head available, right? That's one of the things. Also remember the kinetic energy, the velocity, and the pump is also going to affect, and the atmospheric pressure is also going to affect that, the net positive suction head available. So that's why it's important to know those things so we can be able to solve this problem. So I'm just not going to go over this one yet, but let's go over this other one. So the pump discharge valve is repositioned to decrease cooling water system flow by 5%. So the pump discharge is repositioned to decrease the flow in here. So basically what we are doing, decreasing the flow, we are decreasing the flow, we are increasing the pressure, right? In this case, what's gonna happen here? So if we total the pump discharge, and we are talking about the discharge in this case, so we need to be sure that we know what is this about. So when we throttle down the pump discharge valve, and this is talking about the valve, not this pump, that's gonna increase the net positive suction head available, right? I'm sorry, yes, it's gonna increase. This increases the net positive suction head available, right? And therefore, we are farther away from, this line here. So we're gonna be farther away. So that's good. So now the next one, it says the makeup water containing a high concentration of total dissolved solids, it's added to the cooling water system. So now we have a water that is like dirty, it has dissolved solids. How is that gonna affect? So the presence of that is not gonna like increase, it's not gonna increase the vapor formation within the pump. So, but what we can do is it can, I don't know, it can maybe decrease the temperature, but like the way that I see it, this is unaffecting like the system. So this is also a no. So now let's take a look at B. So if we have service water flow rate is decreased by 5%. So this flow rate here is decreased, right? So what's happening? So if we lower the flow rate from the service water, that's gonna give us a warmer cooling water, right? This one is gonna stay warmer because we have less heat exchanger here. The heat exchanging is gonna get lower. So this one is gonna get warmer because of that, right? So then what's gonna happen? That's gonna increase the temperature. It's gonna increase the temperature here, right? In this piping system, my temperature is increased. So meaning that I'm increasing the temperature that gets through here, right? If I increase the temperature, I'm gonna be closer to saturation, right? And therefore I'm gonna be closer to where vapor formation it's created and that in the impeller. So I'm gonna be closer to that. So I don't want that, but the question is asking which one of these options favors the condition in which we can have gas and vapor binding, and definitely having a decrease the service water, meaning that we increase this temperature here, is gonna get us closer to saturation, Remember PSAT, PI minus PSAT. So we're gonna be closer to that. We don't wanna be closer to that, right? We always wanna have a net positive suction head available that is greater than 0. And it's definitely greater than the net positive suction head required. So the answer for this one, service water flow rate is decreased by 5%. Okay, now this question is just a concept, is P80. If a valve closure suddenly stops fluid flow, the resulting piping system pressure transient is referred to as water hammer, right? If with the valve closure suddenly stops fluid, right? Water hammer. I don't need anything else. I know the water hammer. Okay, now another concept, P381. The major concern with starting a main feed water pump with downstream fluid in a saturated condition is water hammer. We don't want that to happen. We always don't want that to happen. For cavitation, it means that we have a low net positive suction head available, right? Also, thermal shock is going to be affected by temperature, but not pressure. So this one, we haven't talked about that, so that's a no. Okay, next one is going to be P2480, another concept. It says, which one of the following will increase the possibility of water hammer? Will increase venting the liquid not system, systems only after initiating system flow. Yes, that's something that we don't want to do. So that's what's gonna affect it. So this one, we know that we don't want that to happen. Another concept question, P2880 Says the primary reason for slowly opening the discharge valve of a large motor-driven centrifugal cooling water pump after starting the pump is to minimize the potential for water hammer. We already know that, so we've been through that one already. Now we have question P79. Now we touch the subject of cavitation. It says cavitation in an operating pump can be caused by controlling the pump suction valve, right? That's one of the questions. And this is one of the similar questions I think that we already saw. So it says question P149, cavitation of a centrifugal pump in an open system is indicated by, so we have low discharge pressure and low discharge flow rate, right? That's what's going to happen with cavitation. So for cavitation, we already talked about that, is low discharge flow rate and low discharge pressure. Okay, now this question P382. Which one of the following is most likely to cause cavitation in an operating centrifugal pump? So we have our graph. We know, that this is my net positive suction head available. This is my vapor pressure, right? So I already have that information. So it's giving me different options. So what's going to happen if I lower the suction temperature, right? Suction, discharge. If I lower the suction temperature, I'm going to be closer. So let's take a look. So if I lower the suction temperature, the temperature, right? Not the pressure. So that means that I decreased my saturated pressure, but I'm not affecting the eye of my impeller in here. That means that I'm increasing my net positive suction head available. So this one goes up. So what happens when I throttle the pump suction valve? So if I throttle the valve, what's going to happen? I'm actually decreasing the pressure in here at the eye of the impeller. So if I decrease the pressure, what's happening? I'm decreasing my net positive suction head available, right? And that's if I'm getting closer to here, that means that I'm closer to cavitation, and I'm trying to avoid that. So the next one, it says throttling the pump discharge valve. So the discharge valve. That will give me an increase in the pressure here. So I will increase the pressure, I will go up. So I'm increasing my net positive suction head available. If I decrease the pump speed, right, decreasing the pump speed will cause, the flow to be lower in this case. So I'm gonna increase the pressure at the suction of the pump, right? So I'm increasing the pressure at the eye of the impeller, which causes an increase in my net positive suction head available. So the answer is throttling the pump suction valve. If I throttle that, I'm gonna be most likely causing cavitation because I'm gonna be moving my graph like this. So now we have a concept question in P481. While on surveillance rounds, an operator notices that a centrifugal pump is making a great deal of noises, like marbles rattling inside the pump casing, and the pump discharge pressure is fluctuating. The set of conditions indicates that the pump is experiencing cavitation. Just when we hear the marble rattling inside the pump, that's cavitation. Next one, question P1181. Indication of pump cavitation include abnormally, cavitation, we talked about it before, cavitation is equal to low pressure and low flow rate. So Low and low, that's cavitation. Next one, P1381, we already seen that. So cavitation is the formation of vapor bubbles in the eye of the impeller with a subsequent collapse of the vapor bubbles in the casing, right? So that's going to be the answer for this concept question. Next one is P2680. Cavitation is the formation of vapor bubbles in the low pressure area of the pump. Yeah, because the eye is a low pressure area, so it's either one or this one. Followed by the collapse. What's happening to the bubbles? They are collapsing, right? They are collapsing within the pump casing. Next question, P2981. It's another concept question. Pump cavitation occurs when vapor bubbles are formed at the eye of the pump impeller. Then they enter a high pressure region of the pump where they collapse, causing damaging pressure pulsations, like here. We already seen that before. P81, question P81. Okay, let's go over this one. In an operating cooling water system with a constant water velocity, if water temperature decreases, so we have constant water velocity, water temperature decreases, what's going to happen to the volumetric flow rate here, right? So if we have a decrease in the temperature, yeah, we know that if we decrease the temperature, what's going to happen? We're going to increase the density. That's one relationship that we can use. So what's going to happen to our volumetric flow rate? So we have two formulas, right? We have the mass flow rate equal density times volumetric flow rate, but we also know that volumetric flow rate is the area times the velocity of the fluid. So we know that information, right? So it's asking me, so we know that the velocity is constant and the water temperature decreases. What's happening to the volumetric flow rate? What's happening to this? Here, I don't have density. It's not a function of density, my volumetric flow rate. If they were asking me about my mass flow rate, yeah, that's a function of density. That will be affecting my mass flow rate. But in this case, it's not affecting my volumetric flow rate because it says that the velocity has a constant water velocity, right? So yeah, yay for me to know this, but I really don't need that. So the volumetric flow rate is gonna remain the same. It's not gonna increase. It's gonna remain the same, right? Because the water velocity has not changed, right? The water velocity is constant, hasn't changed. So that's gonna be the answer. The answer is not this one because number one, we know that the density has changed, but it's not a function of density. Next question, P281. So now we're gonna start talking about density compensated and not density compensated. So, okay, let's go into the question. So we have a flow instrument that measures the mass flow rate of a steam, often have a density compensation feature because for a steam pressure increase at a constant volumetric flow rate, a steam density will, okay, it's first, density compensation. Density compensation measures a steam mass flow rate, right? I have mass flow rate, it's gonna be equal density times volumetric flow rate. Okay, I know that it says that I have a steam pressure increase. I have a constant volumetric flow rate. Okay, so for steam, if I increase the pressure of the steam, I'm gonna increase the density. Okay, so that means that I'm increasing the density. This remains constant. So what's happening to the mass flow rate? I'm waiting for the answer. So the mass flow rate here is going to increase, right? And then it's telling me, okay, if the steam pressure increases, well, this I already answered this part, steam density will increase as well. I mean, just know that difference, right, for pressure for steam. So now we have question P982. This question says a density compensated flow instrument is being used to measure mass flow rate in a steam system. If the pressure of the steam decreases, indicated mass flow rate will, okay, so let's go part by part. So we have density compensated mass flow rate. So density compensated mass flow rate, we're going to use this formula. Mass flow rate equals density times volumetric flow rate. Then it's telling us the pressure of the steam decrease. If the pressure of the steam decrease, the density of the steam decrease. So if this decreases, then the mass flow rate decreases. So I know that my mass flow rate decreases. So, and it's gonna decrease for all the steam conditions, because in all the steam conditions, my density is decreasing, right? So that's gonna be the answer for that. So now the next question, P1083. For P1083, similar question, but now this one is talking about not density compensated. Okay? So now, a steam generator transient causes main steam pressure to decrease, causes the pressure to decrease, although the actual steam mass flow rate to the turbine remains constant. So the flow rate remains constant. If the main steam flow instrument is not density compensated, the indicated steam mass flow rate will. So what's going to happen here? When we have a system that is, it says is not density compensated, right? It says that usually it says, oh, it's only measuring the volumetric flow rate, right? So in this case, the only volumetric flow rate that is actually that is measured, but in this case we don't have a relation, or we don't have an input for our density. So if the pressure decreases, what's going to happen to my density? My density is decreasing, right? I mean, I can infer that from it. But so I got my mass flow rate is equal to this. But it says, okay, it says that my mass flow rate remains constant, right? My flow rate remains constant. This one decreases. So what is happening to my volumetric flow rate? I mean, it's supposed to be increasing, right? If this was decreases, this one has to increase, to maintaining the same. But the problem here is that this is not density compensated, right? Since it's not density compensated, how can I do this to, figuring it out? How is the flow rate being affected in this case? So remember that in this case, the mass flow rate is going to be proportional to the square root of my differential pressure, right? So in this one, my differential pressure increases, right? But that is supposed to be increasing if my differential pressure increases or that means that my flow rate should be increasing, right? If my differential pressure increases, my mass flow rate is increasing. So in this case, volumetric flow rate, it's going to be proportional also to my mass flow rate. So this one is increasing, right? As well. So my volumetric flow rate is the only thing that should be like measured in this case. So since this one is increasing here, is actually increasing my mass flow rate, right? For what I deduced before, because it's only supposed to be affecting my volumetric flow rate, right? So I hope you can understand this relationship. I hope it was not confusing. So if we have like a density compensated system, or volumetric flow rate will increase, right? Because we need to maintain, or our mass flow rate says that it remains constant. But since we have this relation here, if we increase our volumetric flow rate, we increase our mass flow rate, right? Because we can have this relationship here as well. So that means that, yeah, we are increasing, but why is it increased, right? Remember that it says that, so pressure, it causes the main steam pressure to decrease. The mass remains constant. So the indicated steam mass flow rate is increasing, right? But the volumetric flow rate in this case is gonna be a relation of the velocity. So we can say, oh, what's happening is that we are also increasing the velocity of the steam, right? That's why this is being affected. It doesn't have any, in this case, since it's not density compensated, it cannot be due to the increase of the density in the steam, right? Because it's not density compensated. So this one is a no. That's why it's an increase due to the increase in the velocity of the steam. 82. And in this question, we're gonna just take a look at a relationship between, the same relationship that we've been looking at. Mass flow rate is gonna be equal to density and volumetric flow rate. This is just, trying to do a substitution here. So let's read this. It says a cooling water system is supplying 1 times 10 to the 6 pound per hour of fluor at a certain temperature. So it's giving us this information and it's giving us this, right? Okay, so assuming the volumetric flow rate does not change, so that's going to be important, right? The volumetric flow rate does not change. Which of the following will be the mass flow rate in the system if cooling water temperature increases to 140? So there's a change here. So we went from, so this is what we have. We have the initial, so we have, so we have the initial mass flow rate here that is given. We have the temperature initial and we have temperature final. So that's why we are doing, so, and it says that the volumetric flow rate doesn't change, so we just cancel out the flow rate in here, right? So we just stay with the, this information that we need. But what happens that we are being asked for density, right? So an increasing in the water temperature is gonna give us a reduction in the density. So if we increase the temperature, the density gets lower, right? So how is this change going to affect that? So one of the things that we just need to do that we can do in here is say, okay, I just need to convert my density. So I'm gonna have this formula. Density is equal 1 over specific volume, right? So my new formula is gonna be mass flow rate times the specific volume of the final over the specific volume of the initial, right? And now we need to go to our steam tables and look at the specific volume at 100, right? And at 140 to be able to gather, that information, be able to get our answer. And we're going to end up with the answer of 9.9 times 10 to the 5, which is going to be answer D in this case. So we just need to make sure that, we understand like those relationships. If I'm giving this formula, how can I go in and get the specific volume? Because that's the tool that I have, right? I have the steam table that I can use to get the specific volume. So if I'm giving a temperature, I can go ahead and determine, okay, it's affecting my density. But if I don't have like a density given, like a data of density given, I need to go and get something that is gonna give me the density, right? Like the specific volume. Or what I can do is just go and say, okay, 1 over the specific volume, and just have the density and the density. But why would I just do extra steps, So just go ahead and do it like that. Make sure that you understand your formulas and the relationships, and you'll be good to go. And it will be just matter of just plug and play here. Okay, so we are gonna have similar problems related to that. So there's gonna be similar ones, several of them. But now I just want to go over another of these density compensated problems, because I know it's like a little hard to understand and follow. So let's just go over this one. This one says that a steam generator transient cause main steam pressure to increase. So main steam pressure increase, right? Although the actual mass flow rate remains constant. So mass flow rate remains constant, right? So if the main steam flow instrument is not density compensated, the greater main steam pressure will cause indicated main steam mass flow rate to do what, right? What is going to happen? So what's happening here? So we are not density compensated. So if we are not density compensated, only we are affecting like the volumetric flow rate. But remember, like this gets a little bit interested in here, right? Because we have different formulas, right? We just need to make sure that we know how to do these relationships. So remember, not density compensated, only the volumetric flow rate is measured, right? But there's a way to get there. So what is this telling me initially? It's telling me that my initial mass flow rate is constant, right? So I have a constant mass flow rate. So then it's telling me that the main steam pressure increases, the steam of the pressure is increased, so my density increases, right? So in theory, in order for me to get a constant mass flow rate, my volumetric flow rate will have to go down, right? Theoretically, that's what's happening. So then I have this other formula. So my volumetric flow rate is going to be proportional to my differential pressure. So in this case, if my volumetric flow rate gets lower, my differential pressure goes down too, right? So that's what's happening there. But we also have this other relationship here when we talk about our indicated mass flow rate, and it's going to be here. So if my differential pressure goes down, what's happening to my indicated mass flow rate? Goes down, right? So I kind of like just follow these steps. My step 1, my step 2, and then my step 3 here. That's how I like follow this relationship for having an actual to an indicated mass flow rate, because I know that is only measuring my volumetric flow rate, so I need to do everything in relationship to my volumetric flow rate, right? As you were able to see in here. Just want to make sure that that was clarified. So now let's go ahead and do the next one. The next one is question P3081. It says the volumetric flow rate of cooling water entering a heat exchanger is 500 gallons per minute. So what is this? So 500 gallons per minute. So I have a volumetric flow rate here. So I have volumetric flow rate initial because it's entering. And then it says giving the following, it's giving me the following conditions. I have a cooling water, pressure entering and leaving the heat exchanger at 10 psig. So I have that pressure, right? In and out. So pressure, there's no difference in my pressure or change in my pressure. It's also telling me about the cooling water system. Usually when we're giving like a temperature or a density in just this cooling water system, we need to either go and get the, volumetric flow rate usually. So this is what I got. I have a change in temperature, right? I'm increasing my temperature of my water. So if the temperature of my water increases, what's happening to my density, right? So I'm decreasing my density. So I need to just be sure that I know what relationship to make here, because remember, if we get the density, we can go and get the a specific volume here, right? So we have then this heat exchanger inlet and outlet piping have the same diameter. So things that stay the same, this one and this one. Things that change is this one and this one, right? Then I have my initial volumetric flow rate. So what do I need to do? I know that what comes in comes out, so the initial mass flow rate must equal the final mass flow rate, and the formula for the mass flow rate is density times volumetric flow rate, right? But as I mentioned, I know that my density is equal to 1 over a specific volume, so I just need to substitute this into a specific volume. So I restructure my formula here. And now it's telling me, so what is asking, what is the approximate volumetric flow rate of the cooling water exceeding the heat exchanger? So it's just asking me for the final volumetric flow rate. So I just plug and play basically, and I get this answer of 509 GPM, but I think I jump up some steps. So remember that this information, we can get it on our steam table, right? We can just go and get the a specific volume at saturation temperature for this for my fluid, because I'm talking about water, so it's the fluid. Because I'm gonna have in my steam table, 3 different options, so I'm just gonna use the specific volume of the fluid. So, and then I have this other one that is, gonna be similar. P3783 is just similar to that one, so I can just, go ahead and solve that one. It's gonna be pretty simple. So now I have this question. And now I'm starting getting into pumps now, right? This question is P147, and it's stating that operating 2 pumps in parallel instead of operating a single pump will result in what? So if we put another pump in parallel, right, what's gonna happen? We're gonna be able to do 2 things. Have a higher flow rate and a higher head. So let's take a look at this example. So we have pump 1, we have pump 2. So this is gonna be at this point our head and flow, but since we install the other one, we are increasing, right? Our head, it's increased, and our flow is increased, right? But how relative is gonna be that increase? Because here is asking, it's a large increase, is a small increase, or a large increase. How is this increase going to be, right? So for that, we'll probably need like a better graph. My graph is not the best, but usually if we get we're gonna get a small increase, so the increase in the pump head is not gonna be as large as the increase in the flow rate, right? So we're gonna get a smaller increase in head but a larger increase in flow, right? And this is kind of like the answer to that. And I think it's just a matter of just taking a look at different like graphs, right? Real graphs to be able to notice that pattern, right? But just remember, usually we get a small increase in this part of the head, but a larger increase in the flow. As long as we know that, we're gonna be fine with this question. It's just my drawings. Look at this. It's just, I don't know how to draw. Okay, so the next question is P280. It says the major effect of starting a second centrifugal pump in parallel with an operating centrifugal pump in an open system is increased. So it's basically the same thing. It's asking if I add another CP pump in parallel. We already talked about that. What's gonna happen? What's gonna get increased? Well, I'm gonna increase my head, I'm gonna increase my flow, but which one is gonna have a major effect, right? And we already talked about we're gonna have a major effect on when we increase the flow, right? So the answer is gonna be system flow rate, right? Because we're gonna have a smaller effect on this one. On the system pressure is still gonna get increased, but it's not gonna be as larger as the flow rate. Okay, so the next one, P282. Now we're gonna take a look at positive displacement pumps. The question is to decrease the flow rate through an operating positive displacement pump, an operator should. So what are we supposed to do here? So if I decrease the flow rate on a PDP, so usually this is the graph of the PDP. So I have my head, I have my flow. I have this is my when I'm throttle, and this is my line for my PDP. So the head is not gonna change on a PDP. The head is gonna remain the same, but here I'm sorry, backwards. The flow remains the same, but the head, we can increase the head, right? So the flow stays the same. In this one, if we throttle open, if we throttle close, whatever we move it, the flow's gonna remain the same. We're just basically changing the pressure head in this case. So if what can we do? Like if the flow stays the same, what can we do to actually decrease the flow rate, right? So there's gonna be a relationship where for PDPs we're gonna have proportionalities. So in this case, we know that the volumetric flow rate is gonna be proportional to the pump speed, right? So knowing that, in order for us to reduce, the speed or decrease the flow, what we need to do is, they're giving us the proportionality here. So if we want to reduce the flow rate, we need to reduce the speed, right? So in this case, this was an 80, not a 30. If we want to go from here to here, right, what do we have to do? In this case, it's going to be very simple, right? Decrease the pump available net positive suction head. No, that's not an answer. Throttle the pump. Like if we throttle, that's not going to do anything, right? Because the flow is the same. So the flow stays the same no matter if we throttle anything in here. So the only thing that we know, one of the relationships that we know is the volumetric flow rate is going to be proportional to the speed. So what we need to do is to actually affect the speed. Either if we want to increase or decrease, because we can go the other way around. We can say, what can we do to increase the flow rate in a PDP? If we want to increase the flow rate, we need to increase the speed. right? We want to decrease the flow rate in a PDP. We need to decrease the speed, right? Because this is the proportionalities that are given to for these PDPs. These are PDPs capacities, in their proportionalities. And I think in the pump section we see all the proportionalities for PDPs as well, because there are two more when we talk about also the power, how power is affected, and we will be able to go over that. Okay, so now let's take a look at this other one. In this one, we're gonna actually talk about the head loss, which I think we have already seen information about that, right? So now let's just go over that. So for this is gonna be question P981, and it's asking which one of the following will decrease the head loss occurring in an operating cooling water system? How can we decrease the head loss? But what is the head loss, right? Remember that we have Darcy's equation here. So this is gonna be our head loss, and it's gonna be equal to our frictional coefficient for the piping, the length of the piping, the velocity of the fluid square over 2 times the diameter of the piping times the gravitational constant. So that's gonna be our question. So how can we increase or decrease D? So we need to affect some of them. So the ones that are gonna usually stay the same. So this is a frictional coefficient, and the gravity, this is a constant, is gonna stay the same. So we need to affect this one, or this one in order to have a change on this, right? Can you see that? Okay, so the first one is saying starting a second pump in parallel with the operating pump. So we increase, or we have a second pump in parallel. What's gonna happen? A second pump in parallel is gonna increase the flow rate, right? So because we're in this one, we are assuming, right, that is a centrifugal pump. So we are increasing our flow rate here, and we can go to the previous examples that we have, where we talk about what happens when we have a pump in parallel and series. What are we increasing? So in this one, we are increasing the flow rate. If we had it in series, we're increasing the pressure, right? Just remember those things. So if we increase the flow rate, what is happening, right? The flow rate is going to be affecting our velocity, right? So because it's going to affect our velocity is going to be increasing, right? We increase the flow rate, we are increasing our velocity. So since we are increasing this part on the denominator, our head loss is going to increase, right? So in this one, so the head loss increase, but what I want is the one that decreases. So let's take a look at the next one. So it says shifting to heat exchangers from parallel to series. So shifting to heat exchangers from parallel to series is gonna affect the diameter, right? So what is being affected in here? The diameter, and the diameter is gonna reduce, right? So in this case, if we reduce the denominator, what's gonna happen? We're gonna have an increase on my head loss. So my head loss is gonna increase. That's not the answer though. So okay, let's take a look at the next one. The next one is very simple. It says replacing a 10-foot section of 10 inch diameter pipe with a 20-foot section. So the pipe diameter is the same. We are just increasing the length basically. And it's the same as similar. We are affecting the denominator. We are increasing the value on the denominator. So what's happening here, since we're increasing this value, we're increasing the head loss, right? So that's not it. But if we do the opposite, if we reduce this value, right, of the length, we are kind of reducing this other one. So that's the one that we want. So yes, if we replace, the diameter pipe, if we increase the pipe diameter, we're gonna reduce the head loss. So yeah, that's the answer for this one. Okay, the next one is another pump question. This one is talking about, it says two centrifugal pumps and positive displacement pumps are able to be cross-connected to provide makeup water flow to a system. Each pump will produce 100 GPM at a system pressure of 1000 psig. So if the system pressure is 1200 psig, which one of the following combination will produce the greatest flow rate to the system? Right, so first we need to take a look at what we have in here first. So we're gonna have a centrifugal pump, right? And we have our PDP. We have these two different pumps. They're gonna be doing different things. So these pumps, the PDP and the CP, they're gonna be able to produce, it says, they will produce this volumetric flow rate at this pressure. So both of them will have a volumetric flow rate of 100 GPM. Yeah, volumetric flow rate at this pressure, right? This head. So what is the difference? So the difference here is that the PDP, doesn't matter what we do, is gonna produce, it's gonna give us the same flow. We can change the head, but we're gonna get the same flow, right? And in here, depending on what we do, we can reduce. If we reduce the head, we're gonna be able to reduce our flow, right? So that's gonna be important to know, right? So if we're operating at 1000 here, let's say we're operating here at 1000, we're gonna have a lower flow. If we operate at 1200, we're gonna have a higher flow. We can operate even greater head than that. We can say 1500, we're gonna have a higher flow. So I mean, that's important to know for the PDPs, right? So we can see that in this one, if we vary the flow or the head, we can vary the flow, right? And it's gonna vary inversely, like with the discharge pressure. So that's something important to note. Whereas in the PDP, doesn't matter. So we have 1000, 1200, and 1500, and we're gonna obtain the same flow, right? Here, it doesn't matter. So which one? It says, which of the following combination will produce the greatest flow rate? If we have two positive displacement pumps in series, right? Is that going to produce the greatest flow? So what is going to produce the greatest flow? So the one that is going to produce the greatest flow, so if we have 1000 psi and it's going to give us like 100, and that's what we have here, right, on this one. If we increase this one, right, we're gonna keep getting a lower and lower. So that means that the one that is gonna give us the greatest flow is gonna be a PDP, right? Because no matter if we increase, we're gonna getting the same flow. Whereas in this one, is inversely proportional on my CP. So I know that at least my PDP is gonna be better than having, these two centrifugal pumps in here. So If I have two pumps in parallel, having two pumps in parallel is gonna give me a higher flow rate, right, than it having in series. So having parallel gives me high flow. Series gives me high pressure head, right? So knowing that is asking me the greatest flow rate. So now I determine that my PDP, comparing PDPs to CPs, PDP is gonna give me the greatest flow. But if I connect them either in parallel or series, I know that parallel is gonna give me a greater flow. So if I have two PDPs in parallel, I'm gonna get the greatest flow, right? So, and that's kind of like how I got to that answer on that one. And there's gonna be several questions about that. Like this gonna be a similar one as well. This one is slightly different because it's telling the system pressure of 1,000 psig back pressure. But if the system pressure is like 800, right? Which one of the following is gonna give you the greatest flow? And in here, you just cannot go and say, oh, positive displacement pump in parallel, it gives you the greatest flow. You just need to make sure that yeah, but so parallel, remember, parallel gives you greater flow. Series gives you greater pressure, right? That's one thing to remember. So CPs and PDPs, if we compare them, this one is gonna give you the greatest flow, right? But compared to what? So usually it's depending on the information that you are given here. In this one, what you were given is that you have a system pressure and it was giving you this GPM in here, but the system pressure is different, right? So the system pressure in here is greater. You have a greater system pressure. In this other one, the system pressure is 800. So you are operating above the system pressure. So let's just, for the sake of this exercise, let's take a look at it. So what is happening? So we have, this is my system pressure, right? But if I throttle, right, what's gonna happen? I have this back pressure of 1,000 psig. So okay, so which one is giving me the pressure that is, that is gonna be the greatest flow? I'm gonna have the greatest flow on this one, right? This one is gonna give me the greatest flow, the system pressure. If I have this back pressure at 100 GPM, so I'm gonna be getting less flow. If I compare this with the PDP, it doesn't matter, right? Because for my PDP, the pressure flow, pressure can change. So my system pressure, my back pressure. So this one is gonna give me the same flow. The flow is not changing, right? It's gonna stay the same no matter what. See if you can see in here, but the CP is giving me a higher flow at this system pressure, because we're trying to compare with the system pressure, not this one. Well, I mean, yes, we're comparing against that one, but if we lower the system pressure, this is what we're getting. So we are getting a higher flow rate. Now, in this case, the higher flow rate is going to come from the CP. Now, which one gives us a higher flow? A parallel operation, right? We know that. So now in this case, because, our system pressure is going to be lower, we just need to determine, like, okay, which one is going to give us this higher flow rate in comparison. Like, first we compare CPs with PDPs, and then we go and determine, okay, if it's parallel or series, which one is giving us the highest flow. Okay, so this is how we determine this one. And then these ones are gonna be similar, right? These ones are gonna be slightly similar. The only issue with this one is that we have one that is PDP and one is CP, but the same principles apply to these ones. And then this one is gonna be exactly the same. So this one, it's very easy because we can determine that, okay, which one is giving you the lowest flow, and they are giving you the system pressure, right? And we already saw something related to that, right? System pressure is lower than the maximum design pressure. That's like one of the first ones that we look at. Then we have this other one, and this other one is also similar to that one. So if you see, sometimes like everything is the same. They're just lowering the system pressure. This one is asking the highest makeup flow rate. This one is the lowest flow rate, right? Which one is giving you the lowest flow rate? This one is 2 CPs in parallel. This one, 2 CPs in parallel, and it's gonna depend of these values. You check at the shut-off head. In this one, for instance, you check, your shut-off head, your system pressure, and you compare those things, right? It's gonna be basically the same principle. So that's why I'm not gonna just go over those ones, just because I think we can be able to solve them with the other examples. So now let's take a look at this one. This is the pipe T problem, which is question P 2282. And we have a water at 90 Fahrenheit and 50 psig flowing through a 10-inch diameter pipe at a certain velocity, right? The pipe then splits into two pipes, so that's T. And one is 4-inch and the other one is 8-inch. So we have this 10-inch pipe that is going to split into a T. One is going to be 4-inch, the other one is going to be 8-inch. So that's what it's basically saying. And everything has the same velocity. The velocity is going to be constant. So it says, disregarding any flow restrictions other than the pipe size, which one of the following lists the approximate flow rate through 4-inch and 8-inch diameters? And it says, okay, assume the water velocities are the same. So remember this information is what comes in. It should be the same as what comes out, So what comes in, the sums of this is going to be the same as this, right? And I think we already solved this one before, something similar. So this is the formula that we're going to use. We can use either this one, or we can do it for the other, but we can do for either or. Once we solve either or, if we solve this one first, we're gonna use this other formula to solve for this, right? And that's gonna give us the answer. So it's just a matter of plug and play here. So we know that the answer is gonna be A, because the velocity for this pipe in here, it's gonna be, for the 4-inch, it's gonna be 20. pounds per second. For the 8-inch, it's gonna be 80 pounds per second, right? So that's kind of like how are we able to determine, the velocity, and it makes sense. So if you take a look at this one, it makes sense, right, that it's higher in this one. So now let's take a look at, this one is just similar to the ones that we already saw. It's just making a comparison to CPs in series or parallel, just to determine those things. I think we are good with that. This one is similar to the ones that we saw with the pipe diameter. This one is also similar to that one. This one is similar to the other ones that we have seen. This one, it says, okay, 2 PDPs in parallel. That's easy. Then we have this other one. This one is related to head loss because it's asking about head loss. So as long as we know how to use the head loss formula, right, to make that relationship of the head loss is gonna be equal. What is affecting on my head loss? Since I'm not gonna memorize everything else. I know that what is affecting my head loss is gonna be this. I know that that's not the complete formula because the complete formula has the frictional coefficient for the pipe, and it also has the 2 and the gravitational constant. But honestly, for GPs, that's all that is all the things that are affecting my pipe, like only for GPs, right? And we know that this is a more complete formula for this. So the next one is just gonna, in this one we just need to use the relationship of the volumetric flow rate final over volumetric flow rate initial equal to the differential pressure final over the differential pressure initial. So that's what we need to use in this one, right? And the only difference, so we need to be able to get the differential pressure. So because we are getting here the 10 GPM in here, right? That's what we're gonna be using. We are also gonna be using the differential pressure of 2200, and then we're gonna be using this one. So or differential pressure, because this is the one that stays constant, or pressure on the steam generator because we're talking about a leak in the steam generator, right? So the only thing that we need to do is getting the differential pressure between my RCS and the steam generator. Is my RCS and the steam generator, like the pressure, and also the change, right? The change between the new change of my RCS pressure to the steam generator, because we had a change, right? So this is the before and this is gonna be the after. And well, then you can just go ahead and solve this one using this formula. That one is gonna be as simple as that. Then the next one is similar to the other ones that we have seen. The answer on this one is 2 CPs in parallel. It's asking about the flow rate. Remember, if it's asking the highest flow rate, we know already if it's asking for highest flow rate, it's gonna be parallel. But which one, right? Gonna be able to use these numbers in order to determine if it's gonna be CP or PDP. Then we have this other one, Venturi. This one is just gonna be like more simple, so I'm not gonna just go over that one. I have never seen it also in the GFEs. But then we also have this other one here. This one is gonna be interesting because this one is asking for the lowest initial flow rate, right? Which one is gonna give us? If we're trying to figure it out on lowest initial flow rate, we're probably gonna go over some series, right? So which one are series? This one and this one, right? Because we're looking for the lowest initial flow rate. But in this case, we just need to take a look at, making sure that we know because this one CP is connected to a PDP, and this one we have two CPs in series, right? Two CPs in series and one CP and one PDP. In this case, this one is gonna give us the lowest initial flow rate. If we're just comparing them, remember that in a PDP, the flow rate remains the same, right? But in this one, in the CP, we can vary the flow rate. So, and that's one of the reasons why your answer is gonna be one CP and one PDP in series for this one. And then here we have another T. We have seen this one before, this formula, but now they're using gallons per minute. So we're basically using the same formula, which is gonna be, but now we're using gallons per minute. Right? So this is kind of like the formula that we're gonna use. Instead of using mass flow rate, we use volumetric flow rate. So for this one is a piping that is just changing diameter. So we have a piping that goes like this. It has this constriction. So here we just need, it's a matter of just remember that what comes in comes out, right? Because we're changing just the diameter. This is like 6 inches, this is 4 inches. And what's the formula for this one is 6, like the density times the volumetric flow rate, same density times the volumetric flow rate. And what are we given? And we are giving the volumetric flow rate for this one, right? So what's going to be the final volumetric flow rate? So the density is, they're not giving us anything, so we need to assume that the densities are the same. So that means that the volumetric flow rate is going to be equal, right? We're not giving anything, the temperature is the same, we're not changing the density. Just pay attention to this one, just can be tricky. Then we have this one, T4743. This one is also, we just need to use this formula, right? The head loss, the Darcy equation, and that's all that I use for that one. I don't need to remember everything, just I know that that's what affecting my formula. Okay, let's see if there's anything else new in here. Well, no. Everything else is just basically the same. We can solve it with the information that we been given already. So as long as we know how to solve the previous ones, we're gonna be able to solve this ones here. Right, so we have good enough information. We talk about ventures, we talk about volumetric flow rate proportional to the square root of the differential flow rates. We talk about the Darcy equations here in this one. So yes, and usually like the last ones, they're gonna be talking about the Darcy equation. And I think the one of the very last ones is also kind of like doing a comparison between, volumetric flow rate, what comes in, comes out. We already know that. So we have this water systems, right? So how is it affecting what? And then this one, like, what's the volumetric flow rate in a nozzle and how it's being affected. So we already seen information related to that. So I think we are good to go to solve the rest of them if we want to solve them. But this is basically like all the questions that we will look on the GFEs for the fluid statics and dynamics, section 193006.